Hi YouTube. Today we'll learn about Faraday's law of induction. So what is this equation exactly? What is this epsilon symbol doing here? What are these other symbols? Well, to break it down, this epsilon symbol is EMF, which is the voltage or electric potential produced by the changing magnetic flux, while N is simply a number of turns in wire, which for learning purposes we'll ignore for now. Numbers of turns in wire apply to like a magnetic coil. If you stick a magnet in to the numerous coils. But for now we'll just be looking at singular turns. And magnetic flux I'll explain later. To explain magnetic flux, first we look at Gauss's law, where we see electric flux. So electric flux is basically the surface integral of the electric field going through dA, or an infinitesimally small amount of area, which is equal to this term, but that doesn't really matter in terms of what I'm trying to explain. What does this term mean? Well, that requires some multivariable calculus. So to simplify it, I'll just use a Q here. So basically, the electric flux going through this surface is just equal to the summation of these electric field lines going through, multiplied by the total area of this surface, which is just the side length squared. So whatever electric field lines are going through, let's just call it E. So the electric flux is just equal to E times S squared. So instead of electric fields going through this certain area, magnetic fields are going through that area. And when I was talking about going through that certain area, I was really referring to normal vectors going through that area. So if you have a vector at an angle, the parallel component gets canceled out. So we're only talking about the normal component. So let's say we have this b. For this specific vector, we only take b cosine theta because that is the normal component. So let's try a practice problem. So let's say we have a magnetic field of 10 milliteslas going through a perfect circle of diameter 3 centimeters. What is the magnetic flux? Well, the problem is quite simple. Since all these vectors are traveling in the normal direction, or it's traveling exactly 90 degrees to the area, we set cosine of theta equal to 0, so cosine of theta is just 1. So the cosine theta term does not matter. Because remember, theta is the angle to the normal vector. So if this is the normal vector, n, well, our vectors here are also normal, so theta is 0. So if we take that magnetic flux formula that we found earlier, the area of a circle is pi r squared, or pi d over 2 squared. So that's equal to b pi d squared over 4. So 10 milliteslas is 10 times 10 to the negative third times pi times 3 centimeters, which is 0.03 squared over 4. So if you plug this into your calculator, you would get 7.069 times 10 to the negative 6 Tesla times meter squared. So let's try another practice problem. So let's say we have the same quantities, except this time theta is 30 degrees from the parallel to the area. So we can use that same formula that we had earlier. Magnetic flux equals BA cosine theta. But wait, this theta that we're talking about is a different theta from the theta from our formula. The theta from our formula is to the normal vector, not to the parallel. So our actual theta A is 90 minus 30, which is 60 degrees. So we can start plugging everything back in. So 10 times 10 to the negative third times C. We have pi 0.03 over 2 squared again, then cosine 60. Remember, be careful as to which theta we're using. Remember, it's to the normal, not to the parallel. So plug that into your calculator. And we get 3.534 times 10 to the negative 6 Tesla meter squared. Let's try a practice problem. So let's bring back the original Faraday's law of induction that we had earlier. And then, well, how do we solve this? Well, we know EMF is equal to negative d b a cosine theta dt. But since we know that a and cosine theta are constant, we can bring those out. But we know that b is a decreasing function, so we can find the derivative of b, which is just negative 0.06. So this is equal to negative 0.06 a cosine theta. But then remember, it's positive because of the negative sign. And then a is equal to pi r squared, because it's a circle. Oh, I probably should have mentioned that earlier. And then if you just plug in all of your quantities, we get 1.333 times 10 to the negative 7 volts, because remember, that's what EMF's units are. And then to find current, it's actually quite simple. Just use Ohm's law. IR equals V equals EMF. So I equals EMF over R. Our EMF is 1.33 times 10 to the negative 7th. Our resistance is given right here, so R is 40. So our current is 3.332 times 10 to the negative 9th amperes. So let's try a challenging problem. Let's say we have a perfect square where magnetic field is decreasing, the side length is decreasing, and it's spinning at 0.3 radians per second. So how do we start? Well, let's go to Faraday's law, obviously, where we have negative d ba cosine theta dt. So all of these are differentiable in terms of t, so we can't bring anything out. So let's use the triple product rule. That's b prime a cosine theta plus ba a prime cosine theta plus ba cosine theta prime. So if we have to express this in terms of t, well, let's see. B prime is negative 0.2 if we differentiate that using the power rule. A, well, that's just whatever this quantity is squared, because that's the area of a square. So 100 minus 3t squared times cosine theta. But remember, theta is equal to angular velocity t, because it's kind of like displacement's equal to velocity times time, but in its angular analog. So let's plug that in, and then our omega is just t. Our omega is 0.3. And then we can add, well, let's see here. B is just 1 minus 0.2t. Area prime, well, we can bring back our related rates. So we know that a is equal to s squared. So that means that a prime is equal to 2s times s prime. So a prime, therefore, is equal to 2 times 100 minus 3t times the derivative, which is just negative 3. So that's negative 6, 100 minus 3t. So let's bring that down, times negative 6, 100 minus 3t. And then we take that same cosine 0.3t from earlier. And then for the final one, well, we know that the derivative of cosine wt is just negative w sine wt. So let's add that to the bottom. So we have b 1 minus 0.2t times whatever we have here. So 100 minus 3t squared. And then finally, we have negative w sine 0.3t. And then remember that all of this has a negative sign from here. So that is our final answer.